Hello. Hi. This is lecture 4. Yes, it is. We have just finished lecture 3, which was about why things fall. Well, this is actually a continuation. We're still trying to figure out why things fall, but we've made a lot of progress. We've talked about people trying to figure out why things move, right? The concept of falling is basically moving. But, well, what governs motion, right? What are the laws of nature that are reflected when things move? Well, we had gotten to the point, I'll show some of lecture three's stuff, right? We got to the point where Isaac Newton, building on Galileo Galilei's work, came up with the ideas that would become part of his 3 laws of motion, right? One, the law of inertia, right? Object in motion tends to stay in motion in a straight line unless acted upon by an outside influence. Now that's also momentum, right? Momentum being the amount of something is moving at any given time, a measure of the amount of motion of an object. Inertia, the resistance of an object to motion. Force, right, is the thing that changes momentum. The thing that acts on from the outside is force. And what was really something cool about force? Well, for every action made by a force, there's an equal and opposite reaction that the force winds up creating or producing or exhibiting, right? And if you remember the next point, I'm gonna cover this up over here. This back of the envelope showed us our 3 laws of motion written in math, right? The first law, P equals mv. Second law, F equals ma. Third law, F12 equals minus F21. Now, as we said earlier, right, and this is not new for a lot of you, but for others of you, this is kind of a new concept. Math, right, is just a language. Each one of these equations is essentially a sentence that explains a law of nature which Newton put together. So I took the liberty of writing down what all of those different letters mean on this page, right? It doesn't necessarily mean this on every page. Just like the letter X can stand for a lot of different things, depending on what you're doing or what you're going for, or any kind of variable can stand for a number of different meanings, or even words sometimes, right, have different meaning. In this case, these equations on this back of the envelope are listed this way. So if I were to say these equations in English, right, equation 1, momentum, the momentum of an object is equal to its mass times its velocity, right here, momentum, mass, velocity. Now, most of you heard of these words before, momentum, possibly in a football game or a baseball game. Oh, the momentum is shifted, but it's the amount of motion in some sort of, measurable way. Mass, how much stuff there is of a thing. As you all know, big things can sometimes have low mass, right, like a pillow, whereas small things can have high mass, like a block of lead. So that's a mass, not its volume, not its size, but its mass. And then velocity, right, is a measure of its speed, but with a twist, a very important twist, which we'll get to in a little bit. Okay, F, force, right, in the second equation, this is Newton's second law, the force that an object experiences is equal to its mass, m, times the acceleration that it experiences. Acceleration, right? When we're accelerating from 0 to 60 in a car, right? In my car, it takes like 15 seconds to get there. But I know in some sports cars and stuff, it might get there in 3 seconds or 4 seconds, something like that. But acceleration is how fast you change your speed, right? At what rate are you changing your speed? Again, with a twist, which we will describe in a few minutes. Now, next thing, this third law, F12 equals minus F21. Now, by putting those little numbers after the F, we are specifically talking about the force of one object on another object. So you can see here, right, F12 is the force exerted upon object 2, or object 1 by object 2. And then F21 is the force exerted on object 2 by object 1. So in other words, forward and backwards. And it turns out that they are equal and opposite. And that's why you have this negative, right? F12 equals negative F21. This is Newton's laws of motion expressed in math. again with a twist. And I have one more thing to do. And that's, I mentioned this in lecture 3. I have to put arrows on stuff, right? Let me explain all that. And the remainder of lecture 4 is going to be basically describing Newton's laws of motion, what it means conceptually, what it matters. And then from you, I'm going to ask you in the study guide to start practicing and figuring out how to use these sentences, these equations, to figure out cool stuff about the universe and about things in the human body and about things moving around on Earth. And that question that we started with, why things fall. Okay, I'm going to start putting some arrows down. Okay, watch this. When I put the paper back up, you'll be like, hey, what are those arrows doing there? All right, I'm going to put what the arrows, I'm putting arrows in front of them. In each equation, I'm putting one arrow on one side and one arrow on the other. Notice now that there are these arrows on top. This momentum has got an arrow. This velocity's got an arrow. These forces all have arrows in front of them. And this acceleration has an arrow in front of it. Oh, man. If those of you who are familiar or have had some physics in the past, you'll know what those arrows mean. But if you haven't, let me tell you, those arrows on top of the letter mean that that variable is not just a number, it's a vector. Okay, now, vectors, you have probably remember, how many of you saw Despicable Me? I love that movie, I have to say. It's really sweet, and I enjoyed it. Steve Carell, I thought, was excellent as Groot. A vector is something, it's like an insight that Galileo and Newton came up with, but they weren't the first ones to use it. But they put it in these equations to explain that the direction of things that are moving or things that are being pushed actually matters. All right. And this really makes a difference when you're trying to figure out things like things that are falling or things that are going sideways and so on like that. So a vector, okay, remember Despicable Me again. Vector was the name of the super villain that was being funded by the Bank of Evil, also known as Lehman Brothers, right? Yeah, that's the joke that was going on there. For people who worked at Lehman Brothers who lost their jobs in the Great Recession, doesn't sound so funny. But my point is that was part of the movie. And the Vector, the so-called supervillain, he called himself, he had Vector. He was a Vector because he had both magnitude and direction. Oh yeah, remember that? Oh yeah, right? Vectors, a vector has both magnitude and direction. What does that mean? Those are just words, right? Magnitude and direction. So magnitude, right, is just a fancy word for how big something is. In other words, what is the magnitude of the amount of force? It could be 10 measures, 10 units. Could be 20 units, could be 40 units, right? What are these units? We'll talk about that in a minute. But the magnitude is just how much of it there is. The direction is which way it's happening. Is the motion going this way? Is it going that way? Is it going towards you? Is it coming away from you? That kind of thing. So both magnitude and direction matter when it comes to certain quantities in the universe, including these quantities in the laws of motion. Okay, what does that mean? What does it mean? Let's just go with this question for the second law, Newton's second law of motion, F equals ma. I'll say this again probably later on in the semester, but F equals ma is one of the most fundamental and important equations in all of science. Because what happens is that when people are trying to figure out how a system works, how a machine works, how we work, how the things inside us work, how the universe works, those turn out to be almost always a calculation about how many forces or what kinds of forces are in play and how much mass and how much acceleration is going on in all the combinations that can exist. So F equals ma is really important. So what's F and m and a to do with vectors? Okay, now here's the thing. You probably have experienced this in your life many times, right? So it's not that you're foreign to the concept, it's that you might not have done it mathematically before. But let's say I'm moving this pen this way, right? Now, what happens if I push on it toward the screen, right? It comes towards you. It's going to keep moving this way, but it will also move towards you. So it'll be like kind of like a diagonal. You've seen this before, right? How many times have you done that? Let's say you've got something moving, you're moving this way, a friend comes over, says hi, and kind of pushes you off a little bit. Or, you're like, oh, and you guys all go off to the side, right? There are two things that come in this way and they hit each other at an angle and they wind up coming together, going in a straight line. Turns out that you have to take into account the direction when you are pushing or pulling a thing, right? It matters. If I have a thing moving this way and I have a force pushing against it, right, in the same direction, it'll affect the motion in that direction. If I push it in this other direction, it'll have the effect in the other direction. In other words, direction matters. And when you have a force going on, you have to know what direction it's going and at what angle. Otherwise, you can't figure out where the object is going to go, what direction it goes, and how much it's pushed. That's the magnitude combined together to figure out what the number is. And that's why we call them a vector quantity. Okay. Concept of vectors, very common in our lives. Maybe you haven't done it in math. That's okay. That's the point of doing this class, right? A little bit. You're going to wind up doing some mathematical calculations about forces. So when Galileo was rolling his marbles, for example, down the incline, right? What is happening? The incline actually causes the force that is going straight down, that would have caused the force that would have caused the thing to fall, right? It moderates it a little bit, it slows it down. It causes the force not to be all coming down all at once. It's divided the force. This inclined plane, the little track that Galileo rolls a marble down hundreds of years ago, literally caused the force that is coming down to be split into two directions, right? One direction is along the roll. The other direction is up, perpendicular to the roll. See? So forces get split all the time. And so the answer as to why things fall is because there's a force that goes down. Anytime an object is on the surface of the earth or above the surface of the earth, there is a force that is pulling you down toward the center of the earth. That is what a force is. There's a force that's doing that. If there were no force doing that, and I was just kind of walking and I walked off the edge of a cliff, I would just keep going. But because there is the force that's always acting you downward, either I have to be pushed up, right, the reaction, up from the ground, and thus I will fall. Or if there's nothing to push against that will cause an equal and opposite reaction and keep me from falling, I will go down. I will go down and I will speed up because force equals mass times acceleration. So direction really matters. And as you do some of the homework exercises, you'll see you have to split forces up all the time when you're thinking about how physics is working in a system. Okay, so we take this inclined plane one more time as an example. This is rolling down the hill this way. And that's because the force that is straight down has been split into one that's parallel along the track and one that's perpendicular to the track. Okay. So these are two different kinds of forces. Now, what do we call these forces? Well, okay, let's just draw this inclined plane here. And I'll just put a little marble. Let me use a blue pen for a marble here coming down this way. So it's coming down. This marble, okay, is going to roll down this plane. Galileo, imagine, hundreds of years ago, taking this marble, putting it right here, lets it go, and then it watches it go down, okay? And it's going to watch how fast it goes as it goes down forward. It's not going to fall quite the same speed. Like a ball rolling down won't go as fast as a ball that's being dropped directly. It's because the force on that ball is moderated. It's now coming down this way, and it's also got this normal force, this that's going perpendicular in this direction. And as a result, those two forces add up to the one force coming down. Each individual force is relatively weaker than the other. Okay, that's a mathematical thing that we can work on in just a moment. We won't talk too much about that at this moment. Suffice it to say, though, that there is This force, which we're calling a normal force, I know the word normal doesn't usually in the English language relate to the same thing as perpendicular. But actually in math, the term normal actually does mean a perpendicular or something that's at a 90-degree angle. You may have heard the term orthogonal before. That's the normal force that goes perpendicular to the surface. And then there's this one, the force that's coming down this way. And there are lots of different names for this kind of force as well. Normally, we don't call it the normal force. However, we may call it the parallel force or something like that, or some other name for it. People have different names for it, but that's the force that's causing the motion to come in this direction. The normal force is now pushing against the surface. And these two forces together, if you add them up, will equal the force that would have been put on the object, right? The total force, if it were to fall. In other words, if there were not this inclined plane, or if there were not this track that we're rolling down, this is the force that it would have its motion affected. But it's still feeling that force, but the force has been divided up in these two pieces. Okay. If this is not quite sinking in right now, don't worry about it. Go back, watch this video again. Like I said, it's low production value, but it's just a review, I guess. View it again and get a sense of how these things split up. Okay, and if you think about it some more and you're still not quite sure, maybe the next thing that I say will help sort of explain what I mean by adding up these two forces equals this one force. Okay, and that's the thing about vectors, which is really weird. If you measure the length of this arrow, the length of the arrow is the magnitude, right? Is how much force there is. But if you add up this arrow's length, you add up that arrow's length. So if you add up the length of the normal force and the length of the parallel force, you're not going to get the length of the total force because they add as vectors, which means that there's a geometrical component to this. Things actually wind up adding in right triangles. Okay, that is something that I'm going to talk about now. It's a concept. Think about it, and then you can do some math with it. Okay, let me try to draw that and have you get a sense of what's happening. If, okay, let's say there's a ball that's rolling down a hill and it's coming down this way. Okay, so here's the ball coming down the hill towards you. Let me get a ball. Let me roll it down the hill this way. Okay, here's a football thing. I'm gonna roll it down the hill this way towards you. Okay, everyone go this way. Roll. Okay, it rolls. Trust me, it's rolling towards you. Now, what happens if it gets pushed sideways, right? So this ball here, which was rolling just fine this way, suddenly, another force pushes it this way. Now it has the sum of both of those forces together to create a single force. Remember earlier we were putting the ball, or the marble that Galileo had on an inclined plane, and thus you split the forces up. Now you're adding two forces together. So I'm going to do it this direction. Let's say we have this force and working, it's pushing this way. Okay, so here's a force. Okay, let's call that force A. Little a means it's the first force A coming this direction, that way. And then the object gets pushed a second time. Now another force comes in. Okay, but now this force is pushing this way, and we'll call that force B. All right, force A is coming that way. Force B is going the other direction. What's the net result? What's going to happen if these two forces combine to create one force? How much force is actually being exerted? The answer, which is really cool, right? Let me draw and first make sure and say this. These forces in this example are at 90-degree angle. Okay, if they are at its 90-degree angle like this, So one is pushing east-west and the other is pushing north-south, for example. What happens? The actual total amount of force in magnitude and direction, oh yeah, is the diagonal connecting the two arrows. If I have one force going this way with a certain length in a certain direction and the other force going at a perpendicular 90-degree angle in a different way, right? Then if I draw the arrow from tip to tip like this, and this is the force added, and now's the time to put the arrows on the top and the bottom, right? Because the arrows FA and FB represent the vectors they add by drawing that triangular hypotenuse between the two curves, right? That is really kind of cool. So I'm going to put the arrows here just to be sure, the FA and the FB like that. And then FA plus FB isn't just you add the two numbers, but you actually draw this diagonal, and the net force is this diagonal force. Okay. That's really cool. Again, it's nothing you haven't known in your whole life, right? If you've ever like rolled a pool ball or you play pool or something, it's going this way, and then you hit it with another ball, it'll go kind of diagonally because you added the forces. It'll go that way, right? Not exactly left, right, not exactly forward, backward, but at a diagonal. And this kind of activity, this is how we wind up adding up these vectors. Okay, there's various mathematical ways to do that. It has to do with trigonometry, with angles, sines and cosines and things like that. But the concept is that you put them into a triangle, create a sort of a parallelogram type situation, and then that's how they add, right? And if you think about the reverse of what we had before with the Galileo example, where you have the force of gravity, which would be pull you downward at first, right? And then you have the inclined plane, one going down this way and the other one, the normal force going the other direction. That's how they add. Pretty cool, right? Yeah. So we have arrived at our answer. Almost, right? Isaac Newton said the reason things get faster, the reason they change velocity, right? The reason they change speed is because they're being accelerated. And if we use that F equals ma, force equals mass times acceleration, we see that in order for force to be a vector, the acceleration is a vector too. So how fast you are increasing something, the acceleration, depends on what direction you're going to. And then, wow, the change in momentum here is the change, is the amount of force, right? Multiplied by the amount of time that force is being exerted on the object. Okay, I just combined a couple of concepts there real quick, so don't worry, I'll go over them a little bit, but that's the conceptual idea that I want you to get, okay? Momentum, the amount of motion, and by some measure, is the mass times the velocity, and the force is the mass times acceleration. But acceleration is the change in velocity. So therefore, force is the change in momentum. And the total amount of momentum change that an object experiences is the amount of force it experiences multiplied by the amount of time the force is applied. Whoa, okay, it's all knit together. Again, don't worry about it. If it didn't happen right away, if it doesn't go off, we have opportunities to consider this and go further on this further. Okay, so what does that mean? I'm gonna basically cut to the chase about why things fall. And then we'll go on with additional things about motion and the universe and the human body and things like that. Okay. Things fall because they experience a force from the earth. From the center of the earth, to be precise, there is a mass times acceleration that objects experience when they're on the surface or near the surface of the earth. That's why they fall. They experience an acceleration. There is an acceleration. In other words, what Isaac Newton explained was an acceleration. Something going on that causes you to accelerate toward the center of the earth, causes you to change your speed every time you're anywhere near the earth, a few miles up, right on the surface, in a tunnel, whatever. There's always going to be an acceleration of you toward the center of the earth. Okay? And so you will fall because you are experiencing a force downwards toward the center of the earth. And that acceleration, okay, is gravity. Now, there you go. Gravity, this thing that we talk about all the time in our lives, that we experience and take for granted, right? Gravity, Isaac Newton said, can be expressed as an acceleration. So we experience gravitational force because we have mass, and force is mass times acceleration, right? So the gravitational force each object on Earth experiences is basically its mass multiplied by an acceleration. It turns out that at the surface of the Earth, gravitational acceleration is a certain unit, a certain number. And we used the lowercase letter g in almost all cases to say how much this acceleration is, okay? G is, 9.8 meters per second squared toward the center of the Earth. Now, notice that I put two components. Remember, if you do a calculation in physics and you just put the number, it is incorrect. We do not know that number's true meaning until we actually put down how many of what it actually is. In this case, meters per second squared. Okay, this s to the -2 means per second. That means that if you start at 0 velocity and you let something go in Earth's gravitational field, in 1 second, it will go from 0 to 9.8 meters per second. Okay, 0 to 9.8 meters per second. And then after 2 seconds, it'll have gone 2 times. So 9.8 meters per second plus 9.8 meters per second is 19.6 meters per second. That means that if you've dropped it for 2 seconds, it'll be falling at the end of that 2-second mark at 19.6 meters per second. And because it's a vector, right? Accelerations are vectors. It's always toward the center of the Earth. You have to know this. You have to say the magnitude, which is 9.8 meters per second squared, and the direction. Oh yeah, toward the center of the Earth in this instance. Now, how much is 9.8 meters per second? What is 19.6 meters per second? Because here in the United States, we use feet and stuff like that, miles per hour, we sometimes don't have a really good sense of how much a meter per second is. So I will let you know just for fun. Think about it. 1 meter is about a yard, right? This is about the width of my arms right now. You can't see them because I'm too far away, but it's just about this much, right? It's a little bit more than 3 feet. It's like 3 feet, 4 inches. Thereabouts, 3.36, 39.36 inches equals 1 meter, something like that. Normally, we just sort of say, yeah, it's about 40 inches. Yeah, whatever, close enough, right? Nevertheless, if you go that much every second, think about what you do on a regular basis that would have you go about 3 feet per second. Answer is, well, for example, if I walk slowly, think about it. Every second, if I take a step every second, 1,000, 1,000, that's, a step. Now, how fast is that? 1 meter per second is basically slow walking pace. Okay, we humans, as we walk, if we keep up a pace of 1 meter per second, after about an hour, we will have gone about 2.2 miles. So 1 meter per second is about 2 miles an hour. Okay, so if you guys want to know that, I'll just write that down on this piece of paper again. So, if you ever take a screen grab or something like that, you can get that. But it's 1 meter per second equals about 2.2 miles per hour, like that. Okay, 1 meter per second is about 2.2 miles per hour. And if I say it's about 2, I'm off by about 10%, that gives you an idea how fast I'm going. So 9.8 meters per second, right? That's how fast I'll be going after going, like if I let it go and I count 1,000. At the end of that time, 1.8 meters per second is about 20 miles an hour. So if I drop an object, at the end of 1 second, it'll be going 20 miles an hour. Ooh, how about after 2 seconds, right? Remember earlier we were doing the calculation, 9.8 times 2 is 19.6. 19.6 meters per second is about 40 miles per hour. Oh man, if something drops for 3 seconds, something is free falling for 3 seconds, 60 miles an hour. And 4 seconds, 80 miles an hour. So this is why falling is not a good thing for you. I once made a terrible mistake. I was working in air conditioner, in a window unit air conditioner up on the 3rd floor of our house, and I dropped it. It went out the window, and I was like, "Look out!" Now underneath, fortunately, no one was down at the time. But by the time it hit the ground, it was like went right into the soil, right in the front yard. And we were very lucky that no one was in front of there, because they could have been seriously injured or worse. But by the time it had reached the ground, that thing was going 40, 50 miles an hour, because it had taken just gravity, gravitational acceleration, 9.8 meters per second squared. Okay, so keep that in mind. This is why things fall. And it all relates back to this concept, these laws of motion. We call Newton's laws of motion, how the force works, the dividing of forces into vectors, right? Or the better way to put it, saying that force is a vector quantity, right? And when you're adding forces together, you're not just adding their magnitudes, but you're also adding their directions. And so you use this sort of geometric way to do it. And then Earth's gravity can be expressed as an acceleration. And so we feel gravitational force equal to our equal to our mass times the acceleration of gravity, which is often given by the lowercase letter g. Okay, so going forward, you may see this letter g showing up a lot. Yeah, it's what you expect. But always know that that g is basically a number. Okay, 9.8 meters per second squared at the surface of the Earth, going toward the center of the Earth. That's it. That's why things fall. Sort of. Why? Well, that's a law, right? And remember our nice, beautiful structure of what a law is compared to what a theory is and what data are and things like that, right? So I got to go back at some point and show you that picture of what it means to say that something is a law as opposed to a theory and so on and so forth. Let me see if I can get that. Actually, in that case, I can share it with you. Hold on. Let me see here. Share screen. Here we go. I took the liberty of drawing that thing a little bit. You can see it in the little screen over here. I drew it out a little bit bigger like this, and I digitized it so to make it easier to describe, right? Let's go back and review what we said in lecture 2, right? Where we have the facts going up and sifted over time to create data, right? Because we've added some senses of knowledge or some sense of calculations, mathematics, numbers, and so on to just things we observe. And now we have data. And then we create these laws from there. Can we see patterns in the data that seem to reflect how things work in nature, right? So these laws are Newton's laws of motion, right? And his theory of gravitation is up here. It's a hypothesis, right? He hypothesized that there was this thing called gravity. Now you have to test it. Now you have to make predictions about it, right? We might not need to, but if we really want to know what the scientific theory is, right, we have to make those predictions. We have to attempt to falsify them by experiment or observation, simulation, predict things that are true. And if they're falsified, if we get them wrong, yeah, that's okay. We can try again. It's part of that scientific process, right? We are not just going to say it worked, we're done, because otherwise then we don't predict, we don't attempt to falsify, and therefore it is a non-scientific theory. Or maybe we just say it's unfalsifiable. That's not cool. We don't want that. We want the scientific theory for the purposes of this course, right? And then let me just broaden out the screen to remind everybody. Once you get a scientific theory in, right, it still needs to be continually tested. Even if you say, okay, this scientific theory now adds to facts, right? We now know that this scientific theory is the case. It may still be incomplete. We must understand that we bring it back down here and we repeat the whole process. We say, okay, so this scientific theory has given us these facts, and we now understand what we observed before. We need to get new data. And if there are other laws that we see, if there are other things that happen, or if our hypothesis somehow is falsified under certain cases, then you have to change it. Then you have to adjust the scientific theory. So keep that in mind as we go on in the course and in the semester. Newton's laws of motion and Newton's theory of gravity provides a mathematical laws that allow us to use them. But the actual cause, the actual meaning, the actual reason why that happens still needs to be tested, still needs to be hypothesized, still needs to be shown whether it is confirmed or whether it's falsified. And maybe the bigger idea of what the scientific theory is needs to go back to the drawing board over and over again to find out what it actually is. That, however, is a conversation for another lecture. Thank you all so much for being part of this lecture number 4. Remember, if you've been doing your study guide up to this point, you're partway finished. That's good. And then you'll see that there are several questions and problems, mathematical things where you're trying to exercise your ability to use these laws of physics, these Newton's laws of motion and Newton's law of gravity, to make some calculations, which would be helpful to us as we're figuring out what happens inside our bodies or on our Earth, or maybe even out in space. Thank you so much for being part of this, and I will see you again in the next lecture. Okay, bye. Thanks again. This has been Lecture 4, the continuation of Why Things Fall and/or the actual explanation of Newton's laws. Thank you.